Okay, let's jump in. We're diving into some really fascinating research today, specifically looking at the cutting edge of materials designed to, replace or regenerate bone. Think about those synthetic scaffolds surgeons sometimes use to help bones heal or regrow.
And our source for this deep dive takes us back, actually, to 2010 to a paper published in Acta Biomaterialia. It's titled Improving the Compressive Strength of Bioceramic Robocast Scaffolds by Polymer Infiltration.
Which, okay, despite the technical title, pretty much tells us exactly what we're here to figure out. How researchers tackled a specific challenge in building these bone scaffolds using a technique called robocasting, and how adding a polymer offered a really clever solution to make them stronger.
Exactly. So maybe step one. Why do we even need synthetic bone scaffolds in the first place? Our sources explain that they're incredibly promising because they bypass some pretty big drawbacks of traditional methods.
Right, like using bone from another part of your own body that's an autograft, which means, two surgical sites. Double the recovery, basically.
Yeah, exactly. Or xenografts, which is bone from animals, and those come with risks like rejection or even disease transmission.
Mm-hmm. So these synthetic ones are different.
Right. These synthetic scaffolds act as temporary structures. They provide support for your body's own cells to kind of move in and grow into. And ideally, they're biodegradable.
Meaning they slowly dissolve away over time.
Yeah, as new bone tissue forms, the scaffold disappears,
Ah.
eventually leaving only your regenerated bone behind, hopefully.
Okay, so the paper looks at scaffolds made from materials that sort of fit this bill.
Yes, mainly two types.
Uh,
Ceramics, specifically a type called beta-tricalcium phosphate, or TCP for short,
TCP.
and biodegradable polymers like PLA, that's polylactic acid, and PCl, which is e-caprolactone.
And ceramics like TCP are particularly interesting for bone repair.
They are, yeah. Because they can actually bond directly with bone tissue, which is a huge plus. And they're stiff. They have a high elastic modulus. That means they're better suited if they need to bear some load.
But historically, making these ceramic scaffolds, it hasn't been easy, especially getting the structure right.
That's been the challenge. Using older techniques like, say, solvent casting or gas firming, it made it hard to really control the pore size and, crucially, how the pores connect to each other.
And those pores are absolutely vital, you were saying.
Oh, completely. You need that network of interconnected spaces. That's how cells, blood vessels, nutrients, everything needed for new bone gets inside the scaffold. Without well-controlled pores, the scaffold just doesn't function properly biologically.
Okay, so this is where robocasting comes in. That's the technique they used here.
Exactly. Robocasting. It's a kind of solid free-form fabrication, SFF. Think of it like a very precise form of 3D printing, but for ceramic.
So it builds the scaffold layer by tiny layer.
That's right, directly from a computer design. And what's unique about robocasting for ceramics, as the source points out, is it uses this sort of ceramic ink. And it essentially prints a 3D network of ceramic rods without needing any molds or temporary supports.
Ah, okay. So that gives you much better control over the pore architecture. You can design the channels.
Fantastic control, yeah. You can dictate the macrostructure, the overall layout of those channels for cells to grow through.
But
Uh-huh.
there's always a but, isn't there?
Hey, usually. Even with that control, there's still a fundamental trade-off. The mechanical strength is often limited, and that's directly linked to the porosity you need for the biology to work.
Right. More pores, more space for cells, but less material holding it together, so it's weaker.
Precisely. Which makes it tricky for applications where the scaffold needs to bear some weight initially.
Okay, so that brings us right to the core of this paper. How do you keep that essential porosity for the biological side and make the scaffold strong enough for the surgical mechanical side?
And that's where the idea of polymer infiltration comes in. The paper explores this approach to, boost the mechanical performance. They essentially turn the porous ceramic scaffold into a composite material by filling those pores with a polymer.
And this wasn't a brand new idea in general, was it? Adding polymers to ceramics.
No, not entirely new. It was known that adding a polymer phase could improve properties like toughness and strength in other ceramic structures, even ones made with less controlled methods.
But this specific work was different. They were asking a more precise question.
They were. They wanted to know, what happens if you completely fill the large macroscopic pores of these really carefully made robocast TCP scaffolds with a biodegradable polymer? And they looked at two different ones, PLA and PCl.
And because they started with such a well-defined ceramic structure from the robocasting?
Exactly. That allowed them to really isolate the effects of adding the polymer. They could analyze it more clearly, even using computer simulations, finite element modeling, or FEM, to try and understand why it was working, what the mechanisms were.
Okay, so what did the experiment actually involve? Making the scaffolds first.
Right. First, they fabricated the BTCP scaffolds using robocasting. They had a known porosity around 49% total empty space. That was split between the larger channels between the printed ceramic rods, the macropores, and smaller pores within the rods themselves, the microporosity.
And then they added the polymer.
How? They basically immersed these ceramic structures in melts of either PLA or PCl. The polymers were heated until they were liquid.
So the liquid polymer flows into all the empty spaces.
That was the idea, and they confirmed it using SEM imaging scanning electron microscopy. It showed the polymers did indeed completely fill those designed macropores. And interestingly, they even seeped into some of the open microporosity within the ceramic material itself.
Okay, so now they have these hybrid ceramic polymer scaffolds. The moment of truth. What happened when they tested their strength? Did it work?
Oh, it worked. The results were really quite dramatic. The polymer infiltration led to a substantial increase in the compressive strength, how much squeezing they could take.
How did they compare to the original, just ceramic ones?
Well, when they tested the bare ceramic scaffolds, the ones without polymer, they saw this kind of step-like failure pattern during compression tests, little load drops indicating cracks forming and the structure breaking down bit by bit.
Brittle failure, basically.
Pretty much. But with the polymer infiltrated samples, the tests were much smoother. The load increased much higher before significant failure. The maximum stress values they could withstand were substantially higher.
Okay, substantially higher. How much higher are we talking? Give us some numbers.
Right. So with PCl infiltration, that's one of the polymers, the compressive strength increased by a factor of 3.
3 times stronger, just from filling the pores with PCl.
3 times stronger, yes. Pretty significant.
And what about the other polymer, PLA?
Even more impressive. With PLA infiltration, the strength went up by more than a factor of 6. That's 6.5 times stronger.
6.5 times. Wow.
Yeah, it's a huge jump. The paper gives central values. The strength went from roughly 20 megapascals, let's say 20 units for the bare TCP, to about 60 units for the PCl TCP composite, and up to 130 units for the PLA TCP composite.
That's a massive difference, especially for PLA. And was it just about the peak strength? Or did it help in other ways?
It wasn't just the peak strength, no. The mechanical integrity after the initial cracking started was also vastly improved. Think about it. Even if a ceramic rod breaks, the polymer filling the space around it can still hold the pieces together, bridging the gap.
So it stops it from just crumbling apart immediately.
Exactly. The infiltrated structures could still bear a significant load even after some damage. And the toughness, which is a measure of how much energy the material can absorb before fracturing completely, that increased by more than an order of magnitude.
An order of magnitude, so like 10 times tougher or more?
At least 10 times, yeah. A really big increase in resistance to complete fracture.
And they also mentioned something about reliability improving.
Yes, significantly. They looked at the Weibull modulus. It's a statistical number that tells you how consistent or reliable the material's strength is from sample to sample. And that modulus essentially doubled for the infiltrated structures.
Meaning the strength was much more predictable, less variation.
Much more predictable, yes. It suggests the failure process was becoming more uniform, less influenced by random large flaws, perhaps.
Okay, this is fascinating. So it got much stronger, tougher, and more reliable. And this is where that computer modeling, the FEM analysis, really comes into its own right.
Yeah.
They didn't just show that it got stronger, they could explore why.
Precisely. That's the really cool part. The analysis allowed them to identify 2 distinct mechanisms contributing to this strength increase.
2 mechanisms. Okay, what's the first one?
The first one they call defect healing.
Defect healing. Sounds like it's fixing something that was already wrong.
That's exactly the idea. Remember those tiny surface flaws or micro cracks that naturally exist on the ceramic rods? Even small ones can be weak points where failure starts. The polymer infiltrates these tiny pre-existing defects.
It seeps right into the cracks.
Yes. And by filling them and essentially bonding the walls of the defect together, the polymer makes it much harder for a crack to initiate and spread from those flaws. It increases the stress needed to make that flaw critical.
So the polymer acts like a microscopic filler or glue, reinforcing the weakest spots on the ceramic surface.
That's a great way to put it, microscopic glue. And the analysis suggested that this defect healing effect alone accounted for a pretty significant strength increase. About a threefold boost, roughly.
Just from filling those tiny flaws.
Just from that, yes. And what's really interesting here, this level of strengthening, this threefold increase from defect healing, it was similar for both PCl and PLA.
Even though PLA is much stiffer than PCl?
Exactly. Even though their bulk mechanical properties are quite different. It suggests that for this mechanism, the key factor is simply the polymer successfully infiltrating and filling the defect. If it gets in there and bonds, it's highly effective at strengthening that flaw.
So maybe it strengthens those flaws so much that failure then starts somewhere else.
That's what the evidence suggests. It seems plausible that the original larger surface flaws are effectively healed to the point where cracks now initiate from a different population of flaws, perhaps smaller ones that the polymer couldn't penetrate, maybe because they were too narrow, or perhaps internal flaws within the ceramic rod itself.
And that fits with the reliability improving, right? That Weibull modulus doubling.
It does, yes. The doubling of the Weibull modulus supports the idea that failure is now initiating from a new, more consistent set of flaws after the polymer infiltration masks the original, perhaps more variable, surface defects.
Okay, that makes sense. So defect healing gives about a 3x strength increase, and it works for both PCl and PLA. But PLA gave a 6.5x increase overall. So where does that extra doubling of strength come from for PLA?
Right. That brings us neatly to the second mechanism identified by the FEM analysis, stress shielding.
Stress shielding. Okay, what does that mean?
This mechanism does depend on the mechanical properties of the polymer itself, specifically its stiffness, its elastic modulus.
Okay, so here the stiffness does matter.
Absolutely. If the polymer filling the pores is itself relatively stiff, it can actually carry a portion of the applied load when the whole composite structure is compressed. It effectively shields the ceramic rods from some of the stress.
So it shares the burden, takes some load off the ceramic.
Precisely. The FEM analysis showed this clearly. PLA, which is significantly stiffer than PCl, was able to transfer a good chunk of the load away from the ceramic. They calculated that PLA infiltration reduced the maximum tensile stress experienced by the TCP rod surface by about 53%.
Wow, cut the stress on the ceramic by more than half.
Yes. And reducing the stress on the brittle ceramic directly translates to needing a higher overall load to make it fail. The paper estimates that this stress shielding effect provided by the PLA accounts for roughly an additional twofold increase in the composite's compressive strength.
Okay, so that's the missing piece for PLA's high strength.
That's the missing piece. And what about PCl?
Right, PCl is much less stiff, more rubbery almost.
Relatively speaking, yes. It has a much lower elastic modulus than PLA. And consequently, the FEM analysis showed it provided negligible stress shielding. The calculated stress reduction on the ceramic surface with PCl was only about 1%.
So PCl fills the flaws, which helps a lot.
Yeah.
But it's too soft to really help carry the load itself.
Exactly. It's not stiff enough to significantly shield the ceramic phase from the applied stress.
Okay, so let's put it all together then. The amazing 6.5 times strength increase they saw with PLA infiltration
Is a combination of both mechanisms working together. You get the defect healing effect, which provides about a threefold increase, just like PCl does.
Right.
Plus, you get the stress shielding effect, thanks to PLA's higher stiffness, which provides roughly another twofold increase. 3 times 2 gives you approximately that 6-fold total boost.
And the threefold increase they saw with PCl is basically just the defect healing effect.
Primarily, yes, because the stress shielding contribution from the softer PCl was minimal.
That's a really elegant explanation. It really clarifies why the choice of polymer matters so much for the final strength. So this raises the big question. How good are these hybrid scaffolds? How do they stack up against, the real thing, natural bone?
Yeah, that comparison is crucial for understanding the potential clinical relevance. The paper does address this. First, they point out that even the bare robocast scaffolds, just the ceramic structure made with this advanced technique, were already significantly stronger. About 4 times stronger, they estimate, than conventional TCP scaffolds made using older, less controlled methods when compared at a similar density or porosity.
Okay, so the robocasting method itself gives you a head start just by creating a better, more uniform initial structure.
Absolutely. That controlled homogeneous structure seems inherently stronger. But even with that advantage, those bare robocast scaffolds were still weaker than natural bone at the same density.
Still a gap to bridge then.
Still a gap, but that's where the polymer infiltration really made the difference.
So the hybrid ones got closer.
They did, particularly the PLA-TCP hybrid scaffolds. With that big 6.5x strength increase, they exhibited a compressive strength that was actually comparable to natural cortical bone. That's the dense, hard outer layer of our bones when compared at the same density.
Comparable to cortical bone.
Yeah.
That's a pretty significant benchmark to hit.
It really is. It suggests these hybrid materials could potentially be strong enough for load-bearing applications, which has been a major hurdle for synthetic bone grafts.
Now, the paper also sort of brainstorms a bit about variations on this theme, right?
Right.
Like, do you have to fill the pores completely?
Yes, they discuss some interesting possibilities. For example, what if you didn't completely fill the macropores? What if you just managed to coat the surfaces of the ceramic rods with the polymer?
Would that still help?
Well, theoretically, just coating the surface could still achieve the defect healing effect. You'd still be filling those surface flaws, so you might still get that initial threefold strength increase.
But without the stress shielding, maybe? And leaving the big pores open?
Exactly. You'd potentially get a significant strength boost while leaving the main channels open from the start, allowing bone cells and blood vessels immediate access to infiltrate the scaffold right after implantation.
So that offers a different kind of trade-off.
Yeah.
Maybe less ultimate strength than the fully filled composite, but faster biological integration, perhaps.
That's the potential advantage, yes. A different balance between mechanical properties and biological access. And then there's the potential pathway for the fully filled scaffolds, the ones they actually studied in detail.
The ones where the polymer fills everything. What's the idea there long term?
The idea hinges on the fact that the polymer is biodegradable and typically degrades faster than the ceramic phase. So after implantation, the polymer would slowly resorb in situ, meaning inside the body.
Creating space as it disappears.
Precisely. As the polymer degrades and gets cleared away, it would gradually generate the porosity, opening up those channels after the initial healing phase, maybe. This could allow for bone ingrowth over time, while the remaining ceramic structure, potentially still benefiting from some defect healing, continues to provide support.
So the scaffold sort of evolves its structure inside the body to match the healing process.
Yeah.
That sounds, well, incredibly clever, but also incredibly complex to get right.
It is, and the paper acknowledges this. They present it as a current scientific challenge. How do you perfectly tune the polymer's degradation rate? You need it to match the body's own bone regeneration speed. You want the scaffold to be strong initially when support is needed, but then you need the polymer to get out of the way at just the right time to create space for the new bone to fill in. That synchronization is tricky.
Yeah, I can imagine. Lots of variables there. Okay, so let's try and pull this all together. What are the key takeaways from this deep dive into the source material?
Well, I think first, it highlights that improving the mechanical strength of porous ceramic bone scaffolds is absolutely crucial if we want to use them effectively in tissue engineering, especially for load-bearing spots.
And that robocasting, that 3D printing technique, offers really great control over the scaffold's architecture, the pores and channels.
But that necessary porosity inherently limits the strength of the ceramic alone. It's that fundamental trade-off again.
Right, and polymer infiltration emerges as a really powerful technique to overcome this limitation, basically creating a stronger composite material.
Yeah, and crucially, it works through that dual mechanism we talked about. First, defect healing. The polymer fills tiny flaws in the ceramic, giving a significant strength boost regardless of polymer stiffness, about 3x.
And second, stress shielding. If the polymer is stiff enough, like PLA, it helps carry the load, further reducing stress on the ceramic and adding more strength, another 2x or so.